Welcome students. In this lecture, we are going to talk about separation of variable. So this is a particular type of method which is very beneficial, very important method, yes. And it is quite easy to work also. Okay, so let us understand what's happening here. So let's start with the general linear equation. So let's start with the easy one, yes. A of xy, let's say ux plus b of xy uy equals to 0. Yeah, I'm just starting with some one just to give you an idea. Okay, very simple one. So let's say this equation I want to solve. Of course, we have this method of characteristics which we have already learned. But for this part, what we are going to do is not going to use method of characteristic, but what we are going to do is something called a separation of variable. It means that we want to have the separate variables separate. Yes. So what does that mean? U of xy, we are looking, and you do realize that for this problem, let's call it 1, there are like infinitely many solutions of this problem, right? Yes, I mean, without an initial data and all, there can be infinitely many solutions, yes. So what we basically are doing here is this: we are looking for solution which looks like a function of x times a function of y. Clear? So even in 3 dimension, what happens? It will be, so let's say if you have a problem in R3, let's say, yes. So it may look like this, right? Ux plus 2uy plus 3uz equals to 0, huh? As an example. In that case, what do? You start with this sort of equation equals to a function of x times a function of y times a function of z. You do it like this, yes. You can either choose it like this. So basically what we are doing is we are thinking of it as a, function of x times a function of y, or a function of x and the function of y, sum of it. Okay, so you understand, either it's a product or a sum. We think of it like this. Here also you can think of it like this: x of x plus y of y plus z of z. Now, you may ask, when do we, how do you know that we should start with a sum or a product? That we don't know. Based on the problem, we will just look at it. But for most of the problems, to be very honest with you, we just go with the product. We will see that if the product works or not. Okay, right? Because the sum, see, this particular thing is very restrictive in the sense that, for linear equations, probably you can, but still it won't give, desirable results in most of the cases. But as we are going to see, that the product part, that the product of x times product of y, if you are using this sort of thing, then you can actually derive a lot of different ideas. Okay, so let's start with a basic theory, and then we will work out some problems. So let's say you are given, and I am going to start with the first order equation. You can also do it for nonlinear equation. That's the beautiful part about it. We will look at an example. Okay, so see, as a, let's say, let's put it as a motivation. So what we do is this: we start with the problem given by this: a of x y ux plus b of x y uy equals to c of x y u. Let's just put it this way. Okay, that's the general form of a first order equation. Let's start with it. Now see, any solution of it, if you remember this thing, so if u solves one, then so for every xy, u of xy should satisfy, let's call this as 1, huh? It will satisfy 1, then, and also u should be at least c1, okay, of whatever domain. So let's say this is in omega, so c1 of omega. Yeah. For a global solution to exist, this is what it means. What that means, it means that is u x and u y both exists and is continuous in omega, okay, that is what it means, right, in omega. Now you see what is happening here is this: if now we want to find out the explicit form of this problem. So let's say we are looking at this sort of thing. We are trying to find out, it's a function of x is a function of x, and then y is a function of y. This is the type of problem which you want to solve such that this. So we want u of xy to be this, solves 1. Okay, so you see, if it solves 1, it means u has to be c1. Yes, it means that with respect to x, with respect to y, it has to be continuously differentiable. That will actually imply that x and y both has to be continuously differentiable. Both has to be continuously differentiable. Okay, C1. Of course, continuously differentiable with respect to whatever variable. So, with respect to x or with respect to y. Okay, so I'm not writing that part. Okay, so you see, first thing first, if you want to find a solution like this, the function which you are looking for x and y, you actually have to start with a function which is continuously differentiable at least. Yeah, smooth is fine. Yes, so that's our basic assumption. And then what happens is, once this satisfies this, see, since this solves one, then you always have this problem, right? U of xy, ux of x and y, yeah, plus b of xy, uy means uy of x and y. This is equals to c of xy u, which is a function of xy. This should be hold for all xy in whatever domain omega. Here, so, and this is also true. So this should hold. Yes. So you see, if u of xy looks like this, then for all xy, if you replace it here, this should satisfy this thing. You see, axy, and if you put it here, this is x prime. Yes, y is just a function of y, so uxy does not affect y. So this becomes x prime of x, y of y, plus b of xy, and this, what does it say? It says x of x, y prime of y. Yeah, and then this part you of course have c of x, y, and x of x, y of y. So this has to be satisfied for all xy in omega. I hope you are clear here. Yes. Now you see, by assumption, generally speaking, these coefficients we assume it to be continuous. So basically, if c is continuous, you do realize that y prime has to be continuous, which means y has to be c1. So that's again the idea and the motivation. Yeah. So we want our solution to satisfy this thing. This is the thing which we need to satisfy. Yeah. And once we find such a x, so once we find such a x and a y, we are done. Yeah? Of course, the first thing first is this. See, if c is not 0, so if c is not 0, of course, u equals to 0 does not satisfy the equation. U equals to 0 is not a solution. Is not a solution. Yeah. So what does that imply? It implies that x of x or y of y is not equivalent to 0, right? It means that it is not 0. Okay, so it may happen that for some points in the x domain, or in some point in the y domain, it may be 0, but it can't be equivalent to 0, because if x of x is equivalent to 0 for all x, you do realize that the solution which you are going to get will be equivalent to 0. Okay, which we don't want. We don't want any trivial solution, non-trivial. So basically, we'll assume both x and y are C1 and non-zero. Okay, and non-zero. Let me put it this way. I hope you got the idea. Yes. Okay. Non-zero means it may be 0 at some points, but not 0 everywhere. You understand? Non-zero means not. It means, what I mean is, not 0 for all points in respective domains. In respective domains. Yeah, we don't know what domains they are, but whatever domains they are, they should not be 0 everywhere. Okay, right. So with that in mind, let's just start with an example and see how to work out this sort of problem. So first of all, let's start with a very simple equation, which is a first order linear equation. So ux plus uy equals to 0. This is the equation, and the initial data, so basically the Cauchy data which is given to us is at the on the axis x equals to 0. Yes, u of 0y is nothing but 4 exponential minus 2y. Yeah, that's the equation. Yes, so you see, we are seeking the solution u of xy to look like x of x and y of y, and we want it to be non-zero. Is it okay? See, of course, this problem always 0 is a solution, but again, if 0 is a solution, 0 does not satisfy this one. You understand? So 0 can't be a solution of the whole this equation along with this initial data. Okay, now if this is the case, then what happens? Putting this in this equation, let's just call it 2, let's just call it 3. So putting in 2, we have x prime of x y of y plus 2 x of x y prime of y equals to 0. Yes. So that will imply x prime of x by 2x of x equals to minus y prime of y by y of y. Yes. I hope this is clear. Okay. Now, see, this is very, very important. We have to understand. See, the left hand side of this equation, yeah, is a function of x. So basically, this is only a function of x only. It's not a function of y. And again, this one is a function of y. You understand? So basically, the first one is a function of x and the second one is a function of y, and you are saying they are basically same. Yes. So this is only true if that they are equals to a constant value lambda. Yeah. So this is an, we call it a separation constant. Separation constant. I hope this is clear why it is constant. See, it can't be a function, any function, because the first thing is a function of x, right? So if lambda is a function of x, again the right hand side will be a function of y again. So it does not make sense, right? So what happens is it has to be constant. There is no other way. So it can't be a function of x is equals to function of y. That will imply that both are constants, right? So if that happens, therefore what do you have? You have x prime of x minus 2 lambda x of x equals to 0, and y prime of y minus plus lambda y of y equals to 0. Yeah, so those two. Now, of course, you can solve this problem, right? What is x of x? X of x, if we solve it, we are going to get it is a constant times e power 2 lambda x. And similarly, y of y, we can solve it and we are going to get a constant times e power minus lambda y. Clear? A and b are constants. Huh? A and b are arbitrary constants. Arbitrary constants. We can find out what a and b are because we still did not use our initial data. Okay. So let's write down the general solution. Therefore, the general solution means what? It is basically the family of all possible solutions. Okay. The general solution is given by u of xy, which is x of x times y of y, right? And x of x is nothing but a e power 2 lambda x and y of y is b e power minus lambda y. So if you put it together, it means a constant ab. Let's call that constant as c. ab. So ab, I am writing it as c. Is it okay? So these are arbitrary constants, absolutely no issue. So c times exponential 2 lambda x minus lambda y. I'm just putting everything together. Clear? Okay. Now we have this initial data. U at the point 0y is 4 exponential minus 2y. Since u at the point 0y is 4 exponential minus 2y, okay, and then that is equals to c exponential minus lambda y from here. Clear? So that will imply that c is equals to 4 and lambda equals to 2 is the only such solution, right? Therefore, the required solution which we want is this. Required solution is given by u of xy, which is 4 exponential 4x minus 2 times y. Clear? So this is how, and of course you can check that this satisfy the original equation and the the general solution. Yes, yes. So and you can see that it is very easy, right? It's nothing special is going on. Very, very easy. Yes. So basically what we are doing, if you look at it, you see this is initially in the method of characteristic, you remember we were reducing the problem into an ODE and then solving it. Here also we are doing similar sort of thing. This is a PDE, right? And by writing it in this way, see, we actually reduce it to two different, you see, 2, 1 and 2 different ODE, ordinary differential equation. you use that, you solve the ordinary differential equation and you get your solutions. This is how you do it. Yeah. Okay. Now, so see, let's say a quasi-linear equation, can we solve it like this? Of course we can do it. Yes. And a linear equation, of course, again we can do it. Okay. So what about non-linear equations? Because using the method of characteristic, we did not see how to solve non-linear equations, but I will show you a very, very simple way of solving non-linear equations using this method of separation of variable. Okay. So let's look at a second example. So we have this equation. Let's say y square ux square plus x square uy square equals to xyu, the square of that. Here. Yes. And now again, we want to solve this problem. Yes, I am not putting any initial data. Forget about that. We'll put, oh, maybe we can put it. Doesn't matter. Okay, let's just put it. Yeah, doesn't matter. I mean, you may not put it, but once you put it, it will be, you will get an explicit solution. That's all. Okay, so let's just put this one. Huh? So that's your equation. Let's just call it 2. The equation. We want to find the solution of this equation. Again, what we do is we use separation of variable. Yeah. So this is a function of x times a function of y. Okay. Once you do this, let's say solves 1. Okay. So what do you get if you put all of this together? You have y square, and then u square is x prime of x, y of y, the square of that, plus x square times x of x, y prime of y, and then square of that. This is equals to x, y, x of x, y of y, and then the square of that. That's the equation, right? Now, of course, you can just simplify this thing and we can write it like this: 1 by x square. Yes, x prime of x by x of x, the square of that, plus 1 by y square, y prime of y by y of y, square of that. That is, so basically I am just dividing out with this particular thing, right? And that is going to give you 1. Yes. So this is the thing. Now, you see, we can rewrite this whole thing, right? We can just write it like this, or we can write it like this: 1 by x square. Yes. And then x prime of x by x of x, the square of that, can be written as 1 minus 1 by y square, y prime of y by y of y, square of that. Here. And let's just say that, you see, now we are in similar sort of situation. This part is just a function of x. This part is a function of y. So let's, that will be equals to some lambda. Lambda is some constant. So let's just call it lambda square, because it's just everything is square. Doesn't really matter, but I'm just putting it like this. Okay. So what does that imply? It implies that 1 by x, x prime of x by x of x is nothing but lambda. And we also have y prime of y by y of y. This thing is nothing but root over 1 minus lambda square. Yes. Now, of course, we can solve this equation. So solving, let me put it this way: solving the above. This is ODE, right? We can easily solve it. We solve it and get x of x to be, this is some constant a times x by lambda, right? So it is exponential x square, lambda x square by 2. That's what we are going to get, right? One second, let me check. A equals to, yeah, fine. Yes, lambda x square by 2, I think, yes. And y of y equals to b times exponential. Now, this root over 1 minus lambda square is there. It's basically a mu. You can think of it like this. So y times root over 1 minus lambda square by 2. That's what you're going to get, right? Where a and b are constants. So arbitrary constants. A and b are arbitrary constants. I hope this is clear. Okay. Now, therefore, what is the general solution? The general solution, yes, is basically u of xy is x of x, y of y, right? So if you put it together, I can put it together, a times b, let me write it as c, and then you have exponential this times this. So basically that is lambda x square by 2 plus y square by 2 root over 1 minus lambda square. Yes. I think I made some mistake, no? This should be y square, sorry. Okay. Right. So where C is AB. Yeah. Now, of course, that since u of x0, that initial data is there, u of x0 is 3 exponential x square by 4. If you remember, that's what the initial data we took. Okay. So that will imply that C is equals to 3 and lambda is 1 by, what is it? 1 by 4, right? Half, sorry. Lambda square, right? Half. So therefore, what is your solution? U of xy? The solution will be given by 3 times exponential 1 by 4 x square plus y square root 3. Yeah, so that's your solution. Yes, I hope you understood. So you see, this is quite a complicated nonlinear equation, but using separation of variable, you can easily solve it and get your solution. That's okay. Now, so this is two of the problems where we have used the, product. Now, let me give you another example, example 3, where we don't use the product, but use the sum. Yes. So what we do is this, say we have this equation ux square plus uy square equals to 1. Okay. Let we start with this. U of xy equals to x of x plus y of y be a solution of 1. Solution of 1. Let's just call it 1 on star. Star. Okay. Now, what happens is, now let us put it here. You see, it becomes x of, this becomes ux is nothing but x prime of x, and uy becomes y prime of y. Yes. So then this actually becomes x prime of x, the square of that, plus y prime of y, the square of that, is equals to 1. So that will actually give me x prime of x square equals to 1 minus y prime of y square. See, it becomes so easy, right? So that is equals to lambda square again, the separation constant, separation constant. Because this is a function of x and this is just a function of y, which are basically equal, so it has to be constant. Therefore, what is x prime of x? Essentially, this is lambda, right? Yes, so this is equals to lambda, and again y prime of y, what is it? This is 1 minus lambda square root over. Yes. Okay. Now, of course, you can solve it. So solving all this, we get x of x to be lambda x plus a constant c, 1. And what is y of y? This you are going to get as root over 1 minus lambda square y plus some constant c2. Clear? Okay. So therefore, what the solution which you are looking for, u of xy, should look like this. It is x of x plus y of y. So lambda x plus y times root over 1 minus lambda square plus c1 plus c2. Let's just call it some constant c. C equals to c1 plus c2. Yes, and that will be your solution. So this is the general solution. This is the general solution. Of course, if you have any initial data, you just put the initial data and you have your solution. So you understood, right? It's very, very simple thing. It's just a matter of, so you just put all this, first of all, put the product and put the sum and see which one works. So in this case, this works, right? And it makes life much easier and you can easily solve this equation. Okay. So based on this sort of thing, you can actually see, which part of, which technique is better for you. Yeah. With this, I am going to end this video. Thank you.